Going beyond the moon, the planetary program in 1965 saw successful completion of the Mariner Mars mission. Mariner 4 had to be launched under pressures set by the inexorable timetable of celestial mechanics, which provide only a short window every 2 years during which a Mars mission could be launched. The first attempt was unsuccessful due to a faulty shroud. But 30 days later, in November 1964, Mariner 4 was successfully launched with a redesigned new shroud, on time for its historic 228-day journey to Mars. On its way, Mariner 4 gave us our first look at interplanetary space between Earth and the orbit of Mars. It found it very much like that between Earth and Venus, with one big exception. A notable peak in the impact rate of cosmic dust activity was recorded on the monitors of the Mariner project. This and other interplanetary experiments returned almost 20 million such scientific measurements during the course of the flight. On the 307th day of flight, when it passed beyond effective range for data transmission, Mariner 4 was 191 million miles from Earth, a standing record. It will have a useful life that may extend beyond 1967. As it passed close to Mars, Mariner 4 measured no evidence of radiation belts, such as we have near Earth, and no significant magnetic field. This and the lack of such features as mountain chains suggests that Mars, unlike Earth, may have a solid core. In July 1965, as the crucial flyby approached, tracking stations of the Deep Space Net around the world and the scientists at Mariner Control coordinated the final commands that turned on the cameras. At a range of 10,500 miles, Mariner 4 began to take its pictures. There were 22 in all, and they would cover 1% of the surface of Mars. The picture data were stored on magnetic tape for later playback to Earth. As the spacecraft moved behind Mars, changes in the radio signals passing through the atmosphere of Mars were recorded. This occultation experiment showed the Martian atmosphere to be very thin and revealed the existence of an ionosphere. Picture information in digital form started to come in at 6 a.m. Pacific Daylight Time on July 15th, 1965. Converted to shades of gray, this is what the first picture looked like. A revelation comparable to Galileo's first view of the moon through a telescope. There were 22 pictures taken, the last at a range of 7,500 miles. There was scant evidence of erosion, suggesting that the Martian surface may be as it was 1 billion years ago, with very little water present since that time. Perhaps the best is this one, showing the craters, probably caused by meteors, distributed on Mars in a pattern remarkably similar to that of the moon. After picture playback, Mariner 4 returned to reporting on interplanetary space, with good data received up to last October 1st. Improved ground facilities may make it possible to resume tracking in 1966, and we hope for more good data when Mariner 4 again moves nearer Earth in 1967. The Mariner mission answered many questions, but the big one, is there life on Mars, must wait for Voyager's surface explorations. Mariner data will be used in designing Voyager and in devising the experiments it will carry. Voyager is designed to explore Mars by automated spacecraft and landing capsules which may be later adaptable to other planetary exploration. In 1965, the first part of design definition for the Voyager spacecraft system was completed by each of 3 contractors. The Voyager spacecraft system will orbit Mars to make measurements similar to those made by our Earth satellites. The spacecraft is also intended to carry instrumented capsules, which can land on the Martian surface to make direct biological, geological, and meteorological measurements. Voyager will require planetary quarantine of the landing capsule. In 1965, tests began with a new tool to guard against contamination. In bioclean rooms like this experimental facility, instruments destined for planetary landings may be assembled with minimum risk of bacteriological contamination. This is assured by a laminar flow of clean air from ceiling to floor and by continuous monitoring. Meanwhile, significant planetary exploration continues with a new series of Pioneers under management of Ames Research Center. On December 15th, Pioneer 6 was successfully launched from Cape Kennedy by an improved Delta launch vehicle. This first of the series carries experiments in cosmic rays, magnetic field, solar plasma, and radio propagation. It will send back measurements from up to 100 million miles away in the regions between the Earth and Venus. In 1965, man in space made significant contributions to scientific knowledge. During the Gemini flights that year, astronauts performed a wide array of scientific, applications, and technology experiments. Most spectacular has been the color photography from the Gemini spacecraft. Photographs like these have immense potential for the study of geology, water resources, glaciers, oceanography, meteorology, forestry, and even agriculture. Physiological and biological experiments, in which the astronauts were either subject or experimenter, demonstrated effects of the space environment on man and other forms of life. Some 30 experiments are in preparation for Earth-orbiting Apollo missions, and 10 experiments are defined for emplacement on the lunar surface by an astronaut. These future manned space experiments will require specialized scientific training. In 1965, 5 scientist astronauts were selected and started their training. They are Dr. Owen Garriott, ionospheric physics, Dr. Curtis Michael, nuclear physics, Dr. Harrison Schmitt, geology, Dr. Edward Gibson, engineering physics, and a medical doctor, Joseph Kerwin. Many projects within the complex bioscience program relate to manned space flight, lunar and planetary exploration, or deep space probes. Accomplishments of the bioscience program in 1965 touch upon all of these areas. The first flight model of a biosatellite is now being built and tested. Ames Research Center, manager of the biosatellite program, has assisted experimenters to prepare 13 experiments for the first biosatellite flight, a 3-day orbit. Time-lapse photography shows the test cycle for some experiments to be carried. The effect of weightlessness on growth and movement will be studied using the pepper plant and wheat seedlings. Embryological development will be studied using frog eggs, and the effects of weightlessness will also be studied on the single-celled amoeba. 7 experiments will be flown to study the combined effects of weightlessness and radiation. Bacteria, mold spores, plants, and several insects will be used. This mock-up of the biosatellite shows the spacecraft and experiment configuration for the 30-day mission. In addition to the 3-day flights, the biosatellite will orbit the Earth for periods of 21 and 30 days to determine the effects of the space environment on human cells, rats, plants, and monkeys. The Physics and Astronomy program is of fundamental importance to our national space effort. A family of orbiting observatories under management of the Goddard Space Flight Center is a major element in that program. The first orbiting geophysical observatory was launched from Cape Kennedy in 1964. The second went into a nearly polar orbit from Western Test Range in October of 1965. Both had trouble in orbit. OGO-1 because two booms failed to deploy, and OGO-2 because of horizon orientation problems. Both were officially failures. They must, however, be considered very successful failures based upon the quality and quantity of the data they continue to return. OGO-1 is still operating 15 months after launch. OGO-2, in orbit only a few months, has returned less data, but completed many successful orbits in the fully stabilized and pointed modes not achieved by OGO-1. It continues to give good data in its present spinning mode. Both OGOs have proven their capability to make a broad spectrum of measurements at the same time in the same place in the previously more or less separated fields of ionospheric, plasma, atmospheric, trapped radiation, and magnetic field research. A third OGO has been completed and is now undergoing tests at the contractor. Experience gained with the first two spacecraft has been incorporated into the design and test of this OGO. It will carry the same experiments as OGO-1 and will be launched early in 1966 from Cape Kennedy. The Orbiting Solar Observatory, OSO, is very important to the physics and astronomy program. In orbit above the Earth's atmosphere, it can observe the effects of the sun on Earth and interplanetary space without the blocking effect of the Earth's atmosphere.